Cool. Oh yeah, it's on and there's power. Yeah. Okay. All right, everybody. Here's the plan for this week and for the rest of the semester. It's okay with everybody. We might finish early today. I have to go to a wedding in Roscommon and I have to drive down after college, so nobody's not playing too much. We won't take a break. We'll just keep going. Huh?
Can we go too?
No problem. Yeah, sure. If you like trad music, it'll be great. There'll be loads of brilliant musicians at it. We'll be staying up all night playing tunes until the early hours. It's great. I love being me. Now, so here's the plan for today and for the rest of the semester. So, how many people completed the lab this week? Excellent, great. So I've put the solution, in fact the solution is probably already in there in the master branch, right? If you're looking for it and you don't find it, let me know. But as far as I remember, I did. I merged the branches and I put the solution up. So take the time to have a look at it, right? What we've implemented so far in terms of physics is what's called particle physics, right? And we've done a little bit of a cheat to try and get the orientation to work. And that's a limitation of, particle physics, is that it doesn't take orientation into consideration, particularly not in 3D. We're essentially taking very simple 2D physics and we're applying it to a 3D object. So the one limitation you probably discovered with your lab this week was that the object always has to point in the direction in which it's going, which obviously that doesn't happen in the real world. Do you know what I mean? So you're calculating the look vector from the velocity. And we'll work more on that in the second semester where we do steering. But you can see that even those three simple equations from last week that the three simple equations, you can program a little physics simulation with it, right? The other thing which you can do with particle physics is you can implement what's called a particle system. And that's what today's class is all about. So, can anyone, just in terms of what we did last week, the three most important equations that we did last week. The first one, in terms of implementing what we call a forward Euler integration function. The first one, acceleration equals force over mass. Acceleration equals a force over mass. And force is what's the type of force? Is it a vector, a scalar, a Archimedean matrix? It's a vector, right? It's a vector because force has a direction, right? You can imagine that. And a great way to think about force is imagine a spaceship in space flying and you turn the thrusters on. So it's applying force to the object, causing it to change its acceleration, and indirectly the acceleration can cause the change in velocity, and then that can potentially cause the change in position. I'm sure you probably, well maybe this is intuitive to you, but you can also understand that because force has a direction, it's possible to apply lots of force to the object, but the object doesn't move at all. Isn't that the case? So you imagine a spaceship that's flying like this, and it has thrusters this way and thrusters this way. If you apply thrust in this direction, it will move in this way. If you apply thrust in this direction, it moves in this way. If you apply thrust from both thrusters at the same time, what happens? It doesn't do anything at all. The forces cancel each other out. Alrighty? So that's why force has a direction. So we calculate acceleration is equal to the force over mass. The second equation is we figure out what effect the acceleration has on the object's velocity. So what's the equation for that? Say the velocity is, say delta v is equals to, or v equals v plus, acceleration times time delta. So for how long the, so this acceleration is calculated each time, right? And so we discover that change in velocity is acceleration times time delta. And the third equation is related to how velocity affects the object's position.
Is that the x, delta x?
Yeah, so delta x, in other words, its position is equals to velocity times time delta. And in terms of programming the steering force, what we did in the lab last week, we added a few extra bits. There's the three core equations, but we added a few extra bits. First of all, we decided that if the velocity is greater than a very, very small number, what do we do with it? We use it to calculate the, can you remember? We use it to calculate the look vector, and that way we're saying basically the object is going to look in the direction and in which the object is going to move in the direction in which it's looking. So what we say then is if the length of the velocity vector is greater than the value which we call epsilon, then the look is going to be equal to the velocity divided by the length of the velocity. And that's how you write it. The look is equals to the velocity divided by the length of the velocity. Velocity divided by the length of the velocity is normalizing the velocity into the look vector. So we don't change the velocity, we just normalize it into the look vector. So epsilon, by the way, in programming is just a very small float. And it's in programming because as you guys did IEEE 754 with me in second year, you did? So you know how floating point numbers are stored. You know that floating point numbers can accumulate errors because they're always approximations of the real number. So in order to compare two floating point numbers, it's not enough to say if x is equals to x1 because they might be equal. I mean, one number could be 9.999999, the other number could be 10. Or one number could be 0.000001 and the other number could be 0. They're essentially the same number in floats. And very often when you look at vectors in DirectX, you'll see that it's something like 5.7 blah 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 blah, or OpenGL or any programming e minus 20 or something like that. And you discover it's a really big long number. You wonder, where did they get that number? That number is actually 0. You know, it's because it's the power of 10 to the minus 20. It's an infinitesimally small number, so it's essentially 0. It's just that it has accumulated some errors. You know, you imagine that this thing's getting updated 60, 70 times a second. After a few seconds, floating point numbers, even after one operation, can accumulate tiny errors. These errors all add up. So that's why we compare v against epsilon instead of comparing it against 0. Right? It just checks to see if v has got some value with it. That's where epsilon comes from, right? And so then we can normalize that into that. And then what was the other thing? We calculated the quaternion. Oh yeah, this obviously also is checking to see if it's not equals to 0 as well. Because if the velocity was 0, then this won't work because we'll get a look vector of infinity, right? So you're dividing by 0 there. What was the other thing we did? Oh yeah, we had to check to see if we need to calculate the quaternion. So we're going to use the quaternion to orientate the object. So what do we do? We check to see if the look vector minus the basis vector is greater than, if the length of the look vector minus the basis vector is greater than epsilon as well. So that just checks to see if you've gone off the look vector. The reason why is because when you're calculating the dot product between two vectors, if the two vectors are the same vector, the dot product doesn't make any sense. Do you know what I mean? So you can't calculate a vector which is mutually perpendicular to two vectors if the two vectors are the same vector. So again, the next thing we do to calculate the quaternion is basically to check to see if isn't this what we did? The look vector minus the basis look vector. And then did we calculate the length of that? Or was it the length of it? The length of that vector is greater than epsilon. Then we need to calculate a new quaternion. So the quaternion, in order to calculate it, first of all, we get the cross product of the two vectors to get the base, to get the axis of rotation. So the cross product is going to be axis is going to be equals to the look crossed with the basis, isn't that it? Get the axis of rotation, and the angle is going to be equals to the inverse cosine of the dot product between the look and the basis. Not forgetting, what have we got to do with the axis? Normalize it. You've got to normalize it, right? So we've got to normalize the axis, not forgetting to do that. And then we make the quaternion as the axis angle. Angle axis, isn't that the way the call works? So we pass in, I'll call that theta. So that's going to be between theta and the axis. So that's my calculation of the quaternion. So then I can use the quaternion to orientate the object, and it's going to always go and orientate in the direction in which it's looking. The last thing that we needed to do, that we have to do, can anybody remember what's the last thing we have to do? What will happen if you just do this? You have to reset the force accumulator. Otherwise, it's like turning the thruster on and leaving it turned on, if you want to think of it in those terms. So the last thing you go is the force accumulator is back to the 0 vector, so it's 0, 0, 0. And that's what's called a forward Euler integrator. In this case, it's a forward Euler integrator for a 3D particle. So you can do simple steering. The other thing you can do with these three equations of motion is you can implement what's called a particle system. And a particle system, in fact, I have some notes on this. I might use PowerPoint for this. I think I'll turn on. Somebody just hit the projector, turn it on there. Hit the button. Turn it on. Somebody call. Stand up and hit the on button on it. There we go. Try and get a light to come on.
It says post green.
It says what?
Power is green.
Is the power green? The light is green.
There it is.
Okay, cool. Going on. Thank you. So, yeah, let's take a look at some particle systems to know what a particle system is all about. Alrighty, here's just a few simple particle effects I found on YouTube, which I'm sure you've seen these type of effects in computer games. Just some particle effects. So there's 5 or 6 different particle effects in this short video. So we're not going to program anything as complicated as this. The one that we'll program 2 particle effects. We'll program, just so you know what particle systems are and how you write them from first principles. So typically particle effects are used to do stuff like smoke, to do trails coming out of the back of spaceships, to do blood spurting out of a zombie's brain when you bash it in a computer game. Anything like that where instead of rendering the vertices as being part of a 3D model, in other words the vertices basically represent the vertices of a triangle, each vertex instead is the position of a particle. And there's various ways to actually render the particle system. We're going to do possibly the simplest way to render a particle effect possible, and it's by using what are called point sprites. Mostly these, I would imagine, are probably more complicated rendering techniques. And there's another technique called quads. And I think there are the 2 kind of techniques, but these are simple, well, these are very complicated and beautiful ones. So we'll program the little fountain effect, which you've already seen in the Buddha example. Remember the Buddha thing that we did? So we did the particle effects for that. But they're all basically make use of the same kind of techniques. So that's that one. I'll read another slightly cool one here. Oh, this was a music visualizer of particle systems. Actually, I was thinking of you, Eno, when I saw this one. So it's just a music visualizer of particle system. Goes on for ages. I'll just show you a little bit of it. So lots of other beautiful particle effects. Right, so we'll look at how particle effects are programmed. Yeah, sorry, I did say at the start there that I was going to kind of put the roadmap together. So today's all about particle effects, right? And if we get time, the next thing we're going to look at is what's called Hamiltonian mechanics. There won't be a lab on Hamiltonian mechanics because it's just too hard to actually program it from scratch in 2 hours. So I've written it, and we'll just have a look at what the code does. And then we're going to finish essentially programming all this from scratch, and we're going to start looking at the bullet physics engine for the rest of the course. So we'll look at things like integration, and how to program rigid bodies. And we'll do a couple of applications and look at how to program a vehicle. A very simple vehicle with rotating wheels. And we'll look at how to program a thing called a gravity gun using bullet physics. And that will take us through to the end of the course. Okay, so that's the roadmap. Anyway, so particle physics. Okay, so this is, yeah, we know this. Right? It doesn't take orientation. We can fake orientations, and that's how you fake orientations. So the whole idea behind particle systems, like I say, is that, you know, previously we've been using each vertex, load up a 3D model and render a 3D model, and each vertex on the 3D model represents the corner of a triangle, and we draw a 3D object using a whole lot of triangles, right? Using particle systems instead, we've got lots of small objects, and each small object holds a single vertex, which is its position. And you draw some small object at that position. And that's called a particle system. And you can use these physics equations to model particles in the particle system. And then, as you can imagine, lots of things like smoke, explosions, fire effects, all kinds of special effects. That thing's pretty cool. Look at that thing. That's a thing called volumetric smoke. And simple ones like that, beautiful ones like that, gorgeous things like that, and then rains and stuff like that. They're all particle effects. So each one of those is represented by a 3D vector, and then some physical forces are applied to it. And you can also do stuff like apply transparency to create different physical effects. All this is done in what's called a particle system. And a particle system, its job, number one, is to keep track of lots of particles. It's to create new particles, and you can attempt, you can have some rules to do on how you create particles, where you create the particles. We look at two examples of fountain and the snow effect. And then it's got to update each particle, each frame, typically apply the laws of physics to them, and then has to render them. When particles die, they can respawn again. So that's what a particle system does. So there are several approaches to actually implementing particle systems. The one that we're going to use is a simple, very simple technique called a point sprite. Alright, I'll explain to you how point sprites work. So a point sprite is essentially a quad. Do you know what a quad is? Can somebody tell me what's a quad? What's a triangle? What's a quad? Yay, four-pointed shape, right? So something like a square like this is a quad. And how do you make a quad? How many triangles? Two triangles. So a quad is typically made of two triangles, like this, right? So you can render, God, I'm just realizing. Yeah, we didn't really talk about vertex buffers, did we? Did we mention them at all? Right, when you're rendering a 3D model, we talked about shaders, didn't I? So one of the things that gets passed to a shader in order to actually render an object in 3D is the vertices of the object. So you pass a whole load of 3D coordinates which represent the vertices of a triangle. You pass those to the shader. The shader then applies the model view projection matrices to calculate where that triangle is going to appear in screen space. So the same thing happens with a particle system. You're going to pass a big array to the shader, and you're going to tell the shader to render something that's in that array. And the array is going to contain the vertices of the particles in the particle system. Is that fair enough? The thing is, if you want to, you can use these two approaches. The approach that we're going to use is called point sprites. So when you pass the array of the 3D coordinates to the vertex shader, what the vertex shader will do is it will draw a texture at that position, and it will center the texture at the coordinate that you pass. Does that make sense? The other thing that happens with point sprites is point sprites are also known as billboards. Why would you think they're also known as billboards? What's a billboard? Sure. So they're called billboards. I guess it comes from America. When you drive around America and you see billboards at the sides of the road. The interesting thing about the billboards is, do you ever see a billboard which is facing away from the road? Or a billboard which is facing away from the oncoming traffic? No, billboards always are pointed directly at the road. So when you're driving along, the billboards are always facing you. And the same thing with point sprites. So point sprites are always drawn facing the camera. Okay? And you specify the center, and it will basically draw a small texture at that position. Does that make sense? So that's what a point sprite is, right? There are some limitations with point sprites. One of the major limitations is that if you have a point sprite which is like this size, and you want to draw something like a snowflake or something on the point sprite, right? You're going to specify the center of the point sprite as an XYZ coordinate. You pass that to the shader. If by chance this center point ends up being off the screen somewhere, alright, it doesn't end up getting projected onto the screen, then none of the point sprite is drawn. It doesn't draw any of it at all. So that's one of the limitations of point sprites, okay? But they're fine for the simple particle effects that we want to do. The standard way to do it is to use quads, but obviously with a quad, instead of passing just one vertex, you've got to pass 1, 2, 3, 4 vertices. Alright? And then you actually just draw a textured two triangles. And that's another way to draw particle systems. we're going to use point sprites, right? The other thing then is where do you update the physics properties of the point sprite or of the particle? So obviously you can just do it in the CPU. You can write a C++ program which basically says take the old position, calculate the new position based on the forces, and that's rendering particles on the CPU. The alternative way is to write a shader to do that. You can do it on the GPU. So, but I haven't done this. I've done the quick and dirty way, which is to do it on the CPU. So, very simple one. What do you think the limitation between doing particle effects on the CPU versus the GPU is? What are GPUs very good at? Yeah, they're very good at graphics, but what is it that they do? Parallel. So they're able to parallelize the rendering of the scene. So you might take, 80,000 vertices. Instead of processing one and then doing the next one, you've got a whole load of parallel processing. They're called vector processing units on the GPU that are capable of processing, many pieces of the scene in parallel at the same time. So it's a much better way to do particle systems on the GPU, but you've got to write shaders to do that. And there's an article if anybody's interested in doing particle systems on the GPU. I've just done it the quick and dirty way, which is to just do a C++ program and then send the vertices to the shader. So in BGE, this is what particle effect looks like. So it's just a game component. And then there are two subclasses of game component. One is called fountain effect and one is called snow effect. And then there's a relationship here that the particle effect is actually a one-to-many relationship where a particle effect keeps a list of these particles. And each one of these particles, I should have expanded this out. In fact, I think I have expanded it out in my subsequent slides. What do you think each particle is going to keep track of? Its position. Anything else? There's no such thing as orientation in a particle. Particles don't have orientations. Don't forget, we're drawing these using point sprites or billboards. They're always orientated exactly the same way. There's no orientation. So that's what we're using the simple equations. We haven't really done how to incorporate quaternions correctly into a physics simulation yet. That's the next thing. So what else do you think we need? Obviously position, velocity or speed, and you wouldn't necessarily call it a look vector because they don't as such have a look vector. But they certainly have a velocity. So the particle has got a position, it's traveling in some particular direction. Anything else? What's that? It's color. Yeah? Perfect. How would you implement transparency? Because you want your particles to be at least partially transparent. Huh? Number one, there's a number of things you have to do. How do you do transparency in general in computer programs? I want one image and I want something else to be overlaid on top of it, but I want it to be overlaid in a transparent way.
I grow it with a certain color.
Yeah. Sure. Exactly. You just use 24-bit colors. And you can make your PNG file have a transparent background. So you can do this in GIMP or Photoshop. You can basically say this is the transparent piece of. So typically when we're doing particles in BGE, you specify a particle texture file, something like a PNG with a transparent background. The other thing is you say, sometimes you want to actually also add transparency to the image itself. So what you can do is you can use a 4D color value. So you've got RGB and the fourth value is the alpha, the transparency. Okay, and you have to set up certain transparency flags to tell it to do alpha mapping when you do the rendering. So we've got a particle. What else do you think a particle is going to need to hold? Position, a vector, position vector, velocity, the color, not necessarily the brightness, but it'll have color and it'll calculate that itself. What's that? No, it's going to be drawn using a texture. Alright, so it'll just draw a texture at the X, Y, and Z coordinate. That's how this particle system works. We're just using point sprites. Remember, you can use billboards or quads. In our case, we're using billboards or point sprites. So it'll just draw a texture at that location. Yep. Anything else you think you might need? There's a few other kind of pretty straightforward and obvious, hopefully, things that we need. What's that? Yeah, we're not going to worry too much about the mass, but we might want to store the size of the particle. So sometimes you want particles which are bigger, sometimes you want smaller. For example, if you're doing snowflakes, you're trying to do a scene with snow in it, you might want to have the snowflakes be different sizes, just to create a little bit of randomness. And the other thing as well is you have to decide what's going to cause your particle to die and live. So it's going to have an alive flag. And the other thing it certainly needs, well, it doesn't necessarily need, you have to decide what causes your particles to. I'll tell you what, let's pick the example of the fountain. You've all seen the fountain effect in BGE. So the particles spawn at a central location, they shoot up with some sort of random velocity, and then they go down towards the zero, and then once they hit the zero, what happens to them? Yeah, the transparency increases until you hit the zero, and then what happens? They die, and what happens? They get reborn. As soon as the particle hits the y of zero, you just reset its position and reset all its states so that it spawns again and it'll do the same journey. Does everybody understand that? What about snow?
That's what would hit the ground, you start on top of it.
Exactly. Yeah. So you can see the difference between the snow effect and the particle effect. What's the snow effect starting position? The top, yeah. So its y is going to be some high value. What about the x and z?
Well, then you would be-
Yeah, some sort of random value based on the size of your world. Because you want the snow to look like, you know, if I was to try to make a snow effect in this room, I would want random x and z values, you know, for the x and z, and I want it to be basically the y to start at the top. I want the snowflakes to fall until they hit the ground, and then once they hit the ground, I'm going to respawn them again, okay? With the particle effect, where are we going to start the particles? At the center of wherever the particle system for that is, right? The particles all start at the same place, and then they shoot out with some random velocity. So, the particle effect, what do you think it needs to hold? So, apart from a list of particles, anything else? Because it extends gain component, it's going to get position, it will get everything basically that a gain component has. I thought it doesn't make sense to make a particle extend gain component because it's going to get too much. It's going to get a world transform and everything. It doesn't have a world transform. So, the particle effect keeps a number of things for rendering. You know, it'll keep a reference to the shader and various things like that that are going to be used to render it. So, this is the particle effect class, right? So it has an initialize, update, and draw method. And then it has these two here. Virtual void init particle, and you pass in a particle. What does this mean? Particle ampersand particle. What's that in C++? It's a? No, pointer. No, it's a reference. That just means pass by reference. And the only reason I'm passing by reference, no good reason really. Actually, is there a reason? If I pass it by reference, what can I do to it? I can modify it, and the changes get passed back to the object. So it's not passing a copy of the object. By passing the particle object, what does the equal 0 mean at the end of that? Refer to your C++ notes for a second here. Equal 0 at the end of that means, what kind of function is it? It's a virtual function, and it's a specific type of virtual function? It's a pure virtual function. What does that mean? What's the Java or C# equivalent of a pure virtual function? Almost. It's an abstract class. So that means that you can't, what does it mean that you can't do with a particle effect? It's an abstract class. Can't instantiate it. So you can only instantiate a subclass. If you try and instantiate it, it will say, hey, you can't instantiate an abstract class. And an abstract class is abstract because it has at least one pure virtual function. That's the rule in C++. So you can't instantiate a particle effect. You can only instantiate a subclass of it. And this is a way of kind of designed by contracts. This is basically saying if you want to make a particle system, you have to implement these two methods, or these two member functions. Does everybody understand that? So the other thing that it keeps track of is the list of the particles themselves. This is just an STL list. And I also keep these things here. And you might wonder, well, the particle has its vertex and its color and its sizes. I do this just as a convenience because these vectors get passed into the shader. So I copy these from here into here, each frame, and I pass them to the shader. Sometimes the particles can be alive or dead, and I only pass the ones that are alive. So, and also there's a reason why I use these things here, because basically when you're passing the vertices, the colors, and the sizes to the shader, you have to pass one array of vertices, whereas you can imagine in the particle they're all mixed up together because it's an array of objects. Whereas actually I need a buffer which starts and finishes with the positions. So, whereas you can imagine they're all mixed up in the list. So that's the particle effect, right? The initialize, all it does is loads the shader and binds the vertex buffer objects, uniforms, etc. And the update method just iterates through all the particles, calls update particle for each particle, and then each particle that's alive gets copied into the vectors that we previously had a look, and then those vectors then get passed into the shader in the draw. The other thing as is we also pass in the world view and projection matrices. Now the shader decides what to do with these at a later stage. But the interesting thing is, I don't know if you figured it out yet, but the world is really not necessary in this particular example. Why would the world not be necessary? The world matrix.
Or not.
Oh, they're definitely moving, yeah.
Well, camera's not going to
The camera can move, yeah, definitely. What does the world matrix do? What's the purpose of the world transform matrix?
That's something different.
Yeah, okay.
Scales.
Scales, potentially, yeah. What else does it do? What's its main job? So, like, just to be very clear, like, these are the fundamental concepts in 3D graphics programming and games programming, right? Understanding these three matrices and what they do. So make sure you know what they do, okay? Because it's just really, really important. What does the world transform matrix do? I'm sure we've talked about this on many occasions. What do I make it from? So I want to draw a spaceship. Do I need a world transform matrix? Say I want to draw 100 spaceships, same model, at different positions. What's the purpose of the world transform? Exactly. Okay, so the world transform transforms the object from what space into what space?
3D space and 2D.
Nope.
From
That's what the projection matrix
from
does.
local.
It transforms it from the local space of the model into relative to all the other objects into world. It's called from local space to world space. So in local space, typically your model is centered at 0, 0, 0. That's the center of mass of the object. And then when you do the world transform, it translates it and rotates it. So you take the object's position, quaternion, and you make a world transform matrix out of it. Yeah.
So when the basis is open basis, what comes in the world transform?
But they can potentially if you want it. But the actual object's position, the object's quaternion, okay, they are used to make a world transform matrix. And the shader takes the vertices and multiplies it by the object's world transform matrix to position and orientate it relative to everything else. What's the view project? What does the view matrix do?
Positions,
Got it. Okay, so positions and orientates everything relative to the camera. The camera in view space is located at 0, 0, 0 and looks down the negative z axis. So everything is positioned and orientated relative to that. And the projection matrix, it essentially takes your 3D scene in view space and renders it to a 2D. It's called a clip space. So it renders it in 2D. Okay? The other type of matrix you can have is called an orthographic projection there. And the orthographic projection is similar to the perspective projection matrix. But what it does is it doesn't do what's called foreshortening. It doesn't make faraway objects smaller. Every object is the same size. And that's what the projection matrix does. It makes the faraway objects smaller and the nearer objects bigger. So that's what the draw does, right? So also it sets up the texture and draws the transparency. Oh yeah, but back to the question. Why is the world transform matrix a bit redundant in this case? Think of what the world transform matrix does. What would it indicate if we don't need to use the world transform matrix?
This tries to not care what that other parts really they don't have.
Why would it not care? So we have to draw every particle in the world. What does the world transform matrix do? And think about why we don't need it for this particle
The
system.
particles don't have to be oriented in any direction.
Okay, so number one, there's no orientation, but fundamentally,
No shape differential.
no problem. So there's no scaling and there's no orientation. But what's the fundamental? What's the other thing then that's missing? What's the other thing that the world transform does? Transforms from local space to world space. So if we don't have to transform from local space to world space, that means the particles are in world space. Right? So the particles are already in world space. There's no need to multiply it. There's no local space for a particle. You follow? Particle is already drawn at its x, y, and z coordinate in the world. So if you multiply, there's no world transform. What's the point? Do you follow? So the view and the projection matrices are applied to the particle to, number one, rotate and translate the particle relative to the camera, and two, to apply the foreshortening here. In fact, there's no such thing as foreshortening either. So the projection matrix is probably redundant. But it needs to be transformed from 3D to 2D, so I think it actually needs to be done. But
There would be some only points.
Yeah.
Just the points being further away.
I know, but interestingly, because they're point sprites, The projection matrix, and don't forget it's only one coordinate. So you can apply the projection matrix. All that's going to do is change the 3D coordinates into 2D, but you can't scale a point.
No, but the proximity of them would be closer or narrower together.
Oh, that's true. You're right. Yeah, the proximity of them will be closer and narrower together. But interestingly, you have to use some other way to make the particles appear smaller if they're further away. We'll come to that in a minute.
The actual coordinates have to be scaled.
Yeah, the coordinates have to be scaled. The particle itself, you're right. You're absolutely right. That's a good way of thinking of it. So, a particle, yeah, it does nothing. It just holds the state of a single particle. So there's nothing in the particle apart from this. There's no methods on a particle. So position, velocity, diffuse color, the size of the particle, and these are optional. Sometimes you want your particles to live and die based on how long they've been around for. In both of the examples I've made, I don't use these. But you might decide to keep your particle around for 10 seconds and then get it to respond.
You know what that for the snow then?
Possibly, but I think I just get the snow as soon as it reaches the ground. I basically respawn at the top, which you could basically let your snow live for 5 seconds or whatever.
Yeah,
And then,
melt the ground.
yeah, true, you can leave it on the ground. That's a good idea, and leave it there for a little while. That's actually a better idea. You can say leave it. In fact, that's a great idea. You can modify that. See if it looks nice. And then alive. Okay, just whether the particle is alive or not, because you only want to render the ones where the alive flag is set to be true.
Covered over you.
Well, in fact, again, all I do here is, I think I don't even use that flag. Alright? But it's there in case you want to only render the particles that are alive. So now, the fountain effect. You've all seen the fountain effect? Has everyone seen it? So what the fountain effect does, and this is, whenever people are writing Sprite and particle systems, this is always the first particle system that everybody writes. It's a fountain effect that basically initializes every particle to start at the same position, and then it generates a random velocity. If you think about the velocity on the x and z can be all around in a circle, can't it? But the y velocity, what's the y velocity initially going to be? Well, think about it. Give it an initial starting velocity. Sure thing, but just think about it. Which direction does the velocity vector need to go? The y of the velocity vector. Up. Exactly. So it's the absolute value of whatever random number you calculated. So the x and the z can be often whatever, this way, and the y has to be always a positive one. Otherwise, you get your particles shooting downwards. Do you understand? So you give it an initial starting velocity, and then you just apply the force of gravity to it. So you don't even have to do the force calculation. It's really simple. You just take the acceleration due to the force of gravity is 9.8 meters per second. So you just apply that in the integration for the particle, and that way it will go up, and then acceleration due to the force of gravity will cause it over a number of time steps to eventually change its acceleration so that it accelerates downwards again, and eventually it will start accelerating downwards towards the ground. So that's what the particle effect does. And when it reaches the ground, we respawn it. Another thing that I've decided to implement here, just to make it slightly more realistic, is the particle gets more transparent as it reaches the ground. How would you do that mathematically? What's that? Possibly. I think it's way simpler than a sine wave. Possibly a sine wave if you wanted it to maybe fade very, in a particular way.
It's on its height then.
Yeah, and what do you do with the height? To basically say that, okay, so think about how transparency, by the way, is controlled by the fourth dimension of the diffuse color that's used. So it's RGB A. So that A has to go between 0 and 1. So 0 means 100% transparency and 1 means 0% transparency. So I want that number 0 and 1 to be based on its height. How would you calculate that?
So the 1 would be the maximum height and the 0 would be the one.
You got it, yeah. But just in terms of maths, what would you do?
Increment the fourth value.
Yeah, a tiny bit. That's another way of doing it. Can you just calculate it from the y?
Normalize the y.
Normalize the y. Well, how do you normalize the scalar? Okay, so you got to kind of draw it out, think about it, right? Let's say we wanted to start fading. Let's say my particle here has got a y value, right? And let's say between a height of 20 and a height of 0, I wanted to fade uniformly. At this I want it to be 1, and at this I want it to be 0. Would you guys know how to code that?
Could you have a threshold that keeps bumping up depending on the maximum height of the particle? Then once you start going down, then you take the maximum height.
Yep.
And then use that for
that's exactly what we need to do. But how do you write that in terms of maths and code? So in other words, once it's 20, I have the y value of 20, I want it to be 1. And in fact, if it's 21, 22, I never want it to go greater than 1. So what's that called? Huh? A ceiling. You got it. It is called a ceiling. Right? So you can write ceil. There's actually a function called ceil, C-E-I-L. Alternatively, the function that basically says make it always go between 0 and 1 is called clamp. So you can do some calculation and then clamp it. If it's greater than the maximum value, it's clamped to the maximum value. If it's less than the minimum value, it's clamped to the minimum value. So that's what we want to do. So first of all, we need to clamp it. And the next thing then, how do I get it to vary between, once it's 20, how do I get it to be 1? And once it's 0, how do I get it to be 0?
One decrease it by 1 over the maximum.
You got it. Okay, so that's it. So it's just basically 1 over y. Hang on a sec. 20 over y. It's 20 over y. So it's the height you want it to start fading at. You take y into 20, you get...
The number of units over y.
Yes, the number of units over y. So if you take 20 over y, you're going to get 1. If you take 0 over y, you're going to get 0. And then you clamp it to 0 and 1. So that's how you do the transparency. Particles get more transparent as they reach the ground. So you've seen the particle. I'll show it to you running in code, but basically that's what the code looks like. Oh yeah, here's the init particle. So I put some code in here, right? So radius equals 0.25 f, and then the particle position equals the position of the particle effect. So you set your particle effect position, and that basically says where all the particles are going to spawn from, the position of wherever the particle effect is set to in the world. So you create a fountain effect, add it to your world. It has a position. Every particle gets its starting position from the thing that it's contained in. Okay? Next of all, there we're calculating this initial velocity. So the velocity on the x is random clamped. It's going to give me a random number between minus 0.25 and positive 0.25. A random clamped here gives me a number between 0 and 1. Okay, so if you don't pass any parameters, you get 0, 1 or minus 1 plus 1. I can't remember. This one then, so it must be 0 and 1, yeah? And then random clamped minus the radius and positive the radius. So my x and my z are going to be between minus 0.25 and positive 0.25. You can make them minus 1 and positive 1, but it just makes the particle effect spread out more. Like in this one, I wanted to be kind of narrow, so that's why I constrained it to 0.25 on the x and z, right? And on the y, yeah, I think actually that gives me a number between minus 1 and plus 1. And then what I do is I get the absolute value of the velocity. So it's always a positive number, so the particle effect will always kind of shoot up. Follow? And then the diffuse RGB, is going to be a number between 0 and 1. And I just take, yeah, this doesn't exactly work, but why do you think I'm taking diffuse.org? So first of all, p.diffuse is the particle diffuse. Diffuse is the particle system diffuse. Why do I take the particle system diffuse and multiply it by 0 and 1? What am I gonna get there?
Random color.
Kind of a random color, but the random color is going to be constrained by the thing that it's attached to. So if you have a blue particle effect, if your particle system is blue, what it will do is it will take the blue, the B here, and multiply by a number between 0 and 1. So every particle is going to get a shade of blue. That's kind of what I'm looking for. It doesn't exactly work out though, because sometimes if you mix colors in different proportions, you don't always get shades of blue. But it certainly gives you some control over the color of the particle effect. And then the age of 0 is a lie true. I don't use these. And then the size is a random number between 10 and 50. Just so I can get slightly different, sizes of particles. Is the red light still on that, Victor?
Seems like
Cool.
it is.
Good. So then this is the update particle. So first of all, I have this. What does static here mean in this example?
The same for every single.
Yeah, so don't make the mistake of thinking that static means something that's constant. It can be changed. But what does it mean when you declare a variable as being static in between a function? Does anybody know? Okay, try again. Just have a guess and see what you think. What do you usually use static for? If a variable or member function or a field is static, what does that mean in a class?
Could be used somewhere outside.
Guys, get these right. Yeah, make sure you know these in case you're ever asked them at an interview.
It's like shared between the classes, isn't it?
Yeah, so it applies to the class rather than an instance. But when you use static in this context here, Anybody know? Okay, so I'll just tell you, right? It just means that this variable is only ever created once, regardless of how many times this function executes. And it also means that it retains its value between calls. Okay, so gravity is declared. The first time this function gets called, gravity gets created, and it just reuses it. It just reuses that variable every subsequent time. So it doesn't do this code to initialize it every time around. So okay, it's good to do that. It's a slight optimization. So then the velocity plus equals the gravity multiplied by time delta. So this is me doing this equation here. Acceleration is due to the force of gravity. So that's just that equation there, okay? The next thing then, position equals the velocity multiplied by the time delta, and that's this equation here. Delta x equals acceleration times delta t. There's those two equations that I'm applying to the particle. And then in this case, I take the fade height, right? So I take position dot y divided by the fade height. So it's the y over the fade height. Hang on now, let me think about this, because this is the opposite way around. This is the y over the height. Yeah, does that make sense? Should it be that?
Well, that's going to...
Yeah, it's this way rather than the other way around, isn't it? So let's imagine y is 20. Actually, I'm going to use the actual one. If y was 20, then 5 into 20 is going to be 1. Let's imagine y is 30. Yeah, so it's basically going to be greater then. Sorry, I had this the other way around, and it was wrong. It should be actually the height. It should be the y over the fade height. Yeah, and then if y was 0, you're going to get a height that's 0. So then I clamp it. So I clamp it between 0 and 1. So this alpha is going to go between 0 and 1 depending on the height of the y. And then that's how that would work. So that's my particle effect. That's my particle effect that implements the fountain effect. Is that okay? There's some more interesting stuff with this, and that's to do with how the shader works. So we'll maybe take a look at it. And this is how you use it in code. So you just go fountain equals fountain effect. This number here, which is passed into the constructor, any idea what it's going to mean? It's the number of points you want, right? You can try different numbers here. 500 will render no problem. If you tried 5,000, you'd result in a frame rate drop, okay? Because it's got to do too many updates every frame. Set the fountain effect starting position, and then this is the number that gets multiplied into the diffuse curve for each particle. That's used to render it. And then you just attach it to whatever you want. So let's take a look at what that looks like. I'm sure you've all seen the particle effect and how beautiful it is. Stared at it for hours. So we've got the scene graph game here, so we'll have a look at the scene graph game. So, you've seen this already. This is me basically just creating a particle effect, and I've attached the steering controller, which is stuff we'll do in the second semester. So the particle effect follows a path around the outside of the seed. And that's what the particle effect looks like. Right, what's interesting about this here, you see the way the particle effect is kind of, it's the old particles stay in their old relative positions, even though the particle effect itself is moving. And that's because, when I draw those particles, they're already in world space. I don't apply any world transform based on the object's position. They're not relative to the world. They're just created in world space, and they're drawn in world space. And that's drawn 1,000 particles. And you can see the way they're fading, right? And you can see this is taking the and this case it's the blue and the green colours, multiplying them with some random values. And so that's why you get a slightly bluey-greeny particle system. And they're all slightly different sizes. And you can also see the way that they fade as they approach the ground. So that's how the alpha thing is done. Does that make sense? By the way, why am I spending so much time on particle systems? Can anybody tell me? Not just because they're beautiful, which they are.
They're important.
Huh?
They're important.
Why are they important?
Makes stuff look better.
Huh?
Makes stuff look better.
Yeah, sure. Yeah, why are they important for you guys to know about particle systems? I'll let you think about that one. It's not that complicated. So that's the part. That's that one. The snow effect. The snow effect. The difference between this is to show you. Once you make a particle system, you can generate all kinds of different effects with it, right? So I made the system, And then I did 2 particle effects with it. One being the fountain effect, and then using the exact same code but changing the rules slightly, you're able to get snow. Well, maybe I'll show you what the snow looks like before we go looking at the code as to how we might implement it. So I'm going to add the snow effect here. I think in the snow effect, I don't have a constructor that takes the amount of snow to draw. Oh, can everybody see the beautiful snow? Oh, so Christmassy. Spaceships and snow. So similar rules. Okay, obviously you can see there's different size snow effects. What's the number one obvious difference between the two of them?
Falling in one direction.
Yep.
They're more complicated shape.
Yeah, it's just a different texture. That's all. You know, for one of them, actually, if you want to look at the one for the thing, it's just a circle. It's just a circle. I think it fades a little bit towards transparency. The snow effect is just a texture of a snowflake. So, and it's drawn as a points point. So you see that they're all drawn facing the camera. That's how points points work. All right. So yeah, the other thing then that changes between the snow effect and the fountain effect, the snow effect, instead of starting them all at the same position, I'm starting them at random X and Z's. And then once the same transparency rule applies, you know, I use some value to vary the transparency between the height, and once it reaches the ground, then I set the transparency. You know, I'm doing the same transparency thing. And what's the other difference? Very little difference apart from that.
You said it's always facing the camera.
Yeah.
Situations. If you move the camera around, would you get a side angle like this? I think it would always
Nope.
be facing.
It's always drawn facing the camera. In a way, they're just like sprites. In X and Y sprites, they're always drawn at some X, Y, and Z coordinates, but they're not. It's not a 3D object. It's basically just a texture which is drawn onto the screen underneath your X, Y, and Z coordinates. So it looks, from the perspective of here, if you, for example, change the camera rotation,
Yeah.
so that I rotate completely around here, you notice that my snowflakes are not rotating with me.
No.
My snowflakes are always drawn facing the camera, regardless of what my orientation is. And that's because they're not drawn as 3D objects. They're just drawn as a texture with a position. They're not rotated. There's no quaternion or anything. There's no matrix that multiplies that to apply a rotation to it. Everybody happy with that? What's that? Yeah, it's the exact same rule. They fade to transparent using the same rule as the fountain effect. So it basically takes the Y and then uses that to set the alpha on it. And then once they reach the ground, they are fully transparent and they respawn at the top. So that's how this snow effect works.
So if you just get them training and send people to other objects.
We can't. Without doing them as quads. When you see the shader, you'll see why you can't do that with this particular implementation of the particle system. You could if you wanted to do quads. Wouldn't it be really cool if it actually started snowing outside?
Very hard for you to drag your way.
Yeah, I know. I don't think it's going to happen. It would just be serendipitous if it did. So here's the init particle for the snow. Same thing, so snow effect is a subclass of the particle system as well. So I take its position, instead of taking it relative to the particle system, I just generate, I basically take a range of 1,000. So I basically give it a random X and a Z of minus 1,000 plus 1,000 for the X and the Z. And the Y, I set it to be 1,000. So it starts at 1,000 pi. And then the particle has a random down velocity, right? So I give it an initial random down velocity. So they all look like they're falling at slightly different speeds. So minus the range, so it's very small velocity, so 0.1 f, and then positive 0.1 f on the X and Z. So I maybe don't want them to go exactly straight down. By giving them a little bit of random velocity on the X and the Z, some of them are going to go fall slightly like this, and some of them are going to fall slightly like this. They're not all going to fall exactly straight down. And a really cool thing to do with this particle effect, which I'm sure you've all seen in, if you ever played Call of Duty or Battlefield or any game that's, or what's that game? It had a really cool snow bit and it was Killzone 3. Okay, so there's a really cool kind of area there that was set on, amazing if you ever played that game on a 3D TV, by the way. It looks really cool, and the particle effects look fantastic and everything on a 3D TV. But, you know, occasionally you get like a gust of wind which will blow all the particles off to the side every now and again. That's very easy to implement. Just every now and again, play a sound effect, and then apply some random force to all your particles for a little while, push them over here, and then they'll start falling down. Very easy to do that. So the diffuse. Look at the diffuse color for this one. What does this diffuse color mean? White. Okay, so RGB is white, and then the transparency is 1. So in other words, completely untransparent. And the age, and then the size here, I make these somewhere between 500 and 600. That's just a random size for them, so I get slightly different ones. And then the update particle. So they're the only things you have to change. Update particle and an int particle, and then obviously loads of different textures as well. So again, gravity, velocity, this is exactly the same, right? This is exactly the same as the other fountain effect. The only thing is the fade height is slightly, you know, I use my fade height at 20, so they start fading at 20. That's pretty much it. Right, so there's the two particle effects. Yeah, here's the interesting thing, and I need everybody to pay a lot of attention here to this. Why do I need everyone to pay a lot of attention here to this? What's that? Oh, never say that, but yes. No, but possibly, I don't know, it's a very good candidate question for something that might be important to you guys around about when it's around about January, okay? Whatever date that is. Look at this. This is the shader, and this is the first time I guess have we looked at shaders before? Have we ever looked at the source code of a shader? I think we might have looked at the source code of a very, very simple shader, and these are quite simple shaders as well. There's certain flags that you tell in OpenGL. You basically say, look, these are, when you're passing these here, these are not triangles, these are point sprites. So I want you to draw these as point sprites rather than render them as a 3D object. But then look at the shader code, right? The first line of the shader is hash version 330 core. That's basically saying this version of the shader requires a graphics card which supports at least version 3.3 of OpenGL. And if your graphics card driver is out of date, then this program will crash and say, hey, your graphics card doesn't support OpenGL 3.3. Okay? So that's why you put that line at the top of your shader, and it looks exactly like that. Now these lines here are interesting. Can anybody remember when we talked about vertex shaders? How often is a vertex shader executed? When we're rendering something. Once per vertex. Alright, so this program gets executed once per snowflake that you want to draw. Alright, so if you have 10,000 snowflakes, this short program gets drawn once per snowflake. What you do essentially is you set up your arrays, and your arrays get passed. Your arrays get set up, and the vertex shader will run once for each element in the array. Okay, and the array is called a vertex buffer object. So that's the vertex buffer. In other words, the block of vertices that you want this shader to get run for. So, in fact, there are 3 arrays here, and each of these arrays has got exactly the same number of elements in it. The first array is the coordinates, the 3D coordinates, the x, y, and z coordinates of the particle. The second array is the color, and these are vec4s. So the color I want that particular particle to draw in. And the third one is the point size. So how big do I want to draw that particular vertex? And then these things here, uniform is something that doesn't change for every execution of the shader. These are things that you set up once, and even though you're running this and passing in different array elements each time, these values don't change. That's why they're called uniform. And this is the syntax of the shader. It's kind of the C-like language, right? But uniform essentially means a mat4 means these are 4D matrices. And the GLM language, the GLM header file is based on, that's why it's called a mat4 in GLM, because they're based on the GLSL, which is the shader language for OpenGL, right? They're based on the types for that. So these things are passed in, and MVP is the model, view, and the projection matrices. Model is also known as world. Okay, so model and world, those terms are used interchangeably in different graphics books, right? So, and then this shader outputs a vector4, which is the color. In addition to outputting the position in screen space or clip space, it outputs the color that you want to use to render that thing. So here's the main method here. Okay, so first of all, my matrix, I generate the VP matrix, not the MVP matrix, because I'm not interested in the model. They're already in model space. And I just multiply the projection by the view. When I do P multiplied by V, which one does it do first? It does V first and then it does P. So you specify them in reverse order, and that's how I make my VP matrix. GL position is a built-in word in OpenGL to say this is the position in screen space or clip space. So it's equals to the coordinate with the fourth parameter set to 1. Why do we have to set the fourth parameter to 1? Because it's a 3D vector. I need to make a 4D vector out of it so I can multiply it by a matrix. So I take the VP and multiply it by the coordinate, and that then is going to multiply this and put it into what's called clip space. And then the color is equals to the array element, you know, the diffused element color that you passed in. So, let me see what's next. Yeah, a very interesting thing here. This is very important. Okay, point sprites are always drawn using this GL point size variable. So a simple thing to do would be just to take the point size that's passed in here and then use that to draw the point sprite. Why is that going to introduce a serious bug? What will happen if I just take the point size that's passed in? It won't do what?
With the move difference from the distance from the size.
Yeah, exactly. I want to change the point size based on the distance from the camera. So far away ones I want to draw smaller. Do you understand? So it's not going to do that automatically for you. You have to basically set the point size. How big do I want this sprite to be drawn? And so this is how I do it here. There's loads of ways to do it. I think this is the simplest way to do it. V multiplied by vec4. So basically I take the coordinate and I multiply the view projection. What will that do if I just multiply the view matrix? That takes the position and it orientates it and makes it relative to the camera. Okay? So the camera is located at 0, 0, 0 in view space. So if I just take the coordinate and multiply the view transform, what that's done is it's basically said, here's my camera, here is my position, camera now moves to 0, 0, 0, this thing moves by the same amount. So the camera is located at 0, 0, 0, the position is located at some transformed position based on relative to the camera. So then to calculate the distance to the camera, all I do is get the length of that vector. Does everybody understand? If the camera is located at 0, this thing is moved relative to the camera. Once I calculate the length of that vector, that's the same as if I had the distance from the position to the camera. Does everybody understand that? If you don't understand it, say. It's really important. Everybody happy? Do you understand what I'm getting at, Stephen? Good. Does everybody understand? Will I go around everybody individually and say, do you understand? Stand up. Okay. Do you want me to do a really quick diagram just to show you what I mean?
Yeah.
Okay, no problem. Look at it. If you don't understand, so just say. I don't care. I'm not getting paid a fortune to do this. Can I just grab a page off you?
Oh, okay.
When I show you in the diagram, you'll understand, right?
Yeah, oh, you're doing the opposite. You're really in the world. All you people do.
Right, let's say that is my crude drawing of an eye. That's the camera. And let's say I have two particles in my scene. I have this particle and I have this particle here. I really should have put that nice thing from Father's head up again. When we're drawing these particles, I want this particle to be drawn relative to this one is going to be bigger because it's nearer. So that's why I need to calculate the distance from here to here and use that to control the size, the point size, right? So I need to calculate this distance here. So we know how to calculate distances, don't we? If I have a vector for this, if I call that C and I call that P0, P1, so there's 2 points. How do I calculate the distance from C to P0? I shall leave the room unless somebody answers this one. Never speak to any of you again. Huh? Yeah, but just in vector terms, how do I calculate the distance? A vector represents the camera position, the vector is P0, there's about two vectors with X, Y, and Z coordinates. The length of?
P0. Oh, the vector.
Which vector? Oh, come on, guys. P0 minus C, and then you get the length of that, and that gives you the distance. Does everybody understand that? It's the same as x2 minus x1, y2 minus y1 to be squared, you get the square root of it. Similarly, I could basically take the camera position minus P1 and get the length of that vector, and that will give me that distance. And then I can use that to control the point size, you know. Basically, I want this one to be bigger than this one, so it's going to be 1 over the distance to calculate, you know, the far away ones and near ones and stuff like that. So it's the inverse of the distance, you know, because basically the ones that are closer I want to be bigger, but the distance is going to be
You
smaller.
also use that to work out the speed at which they travel down the street. The bigger ones want to go faster.
No, definitely not. Because the bigger ones are going to go at the same size. Because gravity is the same regardless.
I know, but in terms
Yeah.
of what's rendered on the screen, the bigger ones travel down the screen faster.
Well, the nearer ones
Nearer
will
ones, yeah.
appear, but we don't need to worry about that because the physics will take care of that, right? Now I see what you mean. And the physics will take care of that, which we previously done. We just, when we're rendering it, at this point we're finished with the physics. All we want to do is draw it. So, similarly, you could write these the other way around. You could take that. It doesn't really matter. P0 minus C will do 5. So, an alternative way to do this, I know that I have some matrix, which, and this matrix, basically, this is my x, y, and z. The camera in view space is always located at 0, 0, 0, and it looks down the negative z-axis. So let's imagine my camera was here, my point was here. I translate the camera, goes down to 0, and then the point goes down to here. Do you understand that? That's what the view transform matrix does. Does everybody understand that? All right? So can you see now that if you take this, multiply by the view matrix, you're going to move it down to here, and then all you need to do to calculate the distance from the camera, if the camera was up here, is just calculate the distance, that length there, the length of that vector. Everybody understand that now? So that's the same as the distance from the camera to the point. Does that make sense? Is that better?
Just so clear,
Yeah.
you move it down to 0, 0, 0 to calculate the distance. It's easy to calculate the distance from 0, 0.
No, it has to be done anyway.
Oh, it has to be.
Well, I mean, this is exactly the same. If you take P0 minus C, what I've done is I've taken C minus C, and that becomes 0, 0, 0. And then this is just subtracting the same thing. An alternative way to do this is instead of just subtracting the camera position, you just multiply by the matrix, the view matrix. And that's what the view matrix does anyway. The view matrix translates everything relative to the camera. So if the view matrix, if you take the camera position, you multiply by the view matrix, the camera position goes to 0, 0, 0. Everything else moves relative to the camera. Okay, so like I say, if your camera started up here, your position was here. When you do the view transform matrix, the camera goes to 0, 0, 0. Everything else moves by the same amount. So like I say, yeah, you just multiply by the view matrix, then calculate the distance. And then I'm just using this to take the point size that's passed in and multiply by 8 over the distance. So I'm just scaling it based on the distance. So the further away it is, the points are going to be drawn smaller. It's very easy to modify this shader and see what happens if you don't do that. That's the vertex shader. The fragment shader is nothing. It doesn't do anything. But it's interesting to just look at it, because this is a very typical fragment shader. It doesn't do a whole lot. How often does the fragment shader work? Once for every fragment. What's a fragment? What are fragment shaders called in DirectX? They're called pixel shaders. So the fragment shader executes once per pixel, or once, I think it's once per pixel essentially, right? So anyway, what gets passed in, the GL position gets passed in. The purpose of the fragment shader is just to decide what color to draw on a particular pixel on the screen. And this is what essentially it's doing here, is it is sampling the texture. That's what this does here. It samples the texture to figure out what color to draw. It obviously has to sample the texture to figure out, you know, if it's drawing a filled pixel or an unfilled pixel. And that's how this works. It uses a thing called sampling. And the point coordinate is the thing that gets passed into the vertex shader to basically say what's the 2D point. And then I multiply it by the color that gets passed in by the shader, the vertex shader as well. So that's why I'm taking the texture and I'm also multiplying it by the diffuse color that gets passed in. The diffuse color that gets passed in, don't forget it's 4D, so it's going to have the alpha. And this is how, it's not just the texture, it's actually taking the texture multiplied by the alpha. It's interesting to modify these shaders very slightly just to see what effect it has, right? And I'll show you what happens if you don't do those things, and then we'll finish. So first of all, there's my two special effects. Again, there's the original versions of them. So the first thing I'm going to do, just to show you what happens if you don't do these shaders correctly, or what the purpose of the shader is. These are my particle shaders. If you look at the vertex shader, first of all, let's just do this instead. Let's just take the point size as it's passed in, and don't make the point size smaller. So the point size now, it's not going to do anything with it. It's just going to take the point size that gets set up when you set up the particle, and watch what difference that makes. It means that all particles are drawn at the same size. So we get giant snowflakes. And also look at this guy. So there's something weird happening with the transparency here that didn't used to happen. So I've obviously screwed something up. I need to look into that. But look what happens when you move away. It just looks like a blob. A blurry blob. So that's why it's important to take the size of the particles drawn using this technique and to scale them based on the distance from the camera. So that's the first thing you can do. So if I put this back in here, and instead I go in and I have a look at the fragment shader, and I change the fragment shader just to do the sample from the texture, not to use the color that gets passed in and multiply it. Then the particle effects are going to work fine, but there's no transparency anymore. Oh, in fact, yeah, all it's going to do now to render that particle is it's just going to use the particle, it's just going to use the texture. So again, you can see there's no transparency on any of these things as they approach the ground, and also it's not using the diffuse color that gets passed in. Basically change the shader, so it's not multiplying the sampling by the diffuse color for that particular texture. Alrighty. So that's a crash course in how particle systems work, right? So most importantly, before we figure it out, what does a particle system do as opposed to rendering a 3D model? What does it do? Keeps track of? Yeah. Good man. But just remember it, right? It's important. Now, and equally, if you ever need to write a particle system yourself, I've written a few particle effects. You know, I wrote one before for DirectX, and this is kind of a model on it, but this is way better, because this has the transparency and the shaders and everything. So the particle system, as opposed to rendering a 3D model, each vertex represents the position where you're going to draw something. You know, and in this example, we're going to use this technique called point sprites or billboards. But particle systems can also use. What else can particle systems use to do more realistic rendering? They can use quads. So instead of just passing in a single thing, you actually just draw a textured quad and you work out all that stuff yourself. And this is a quick and dirty way to do particle systems, and particularly simple particle effects when you're doing using this. And just remember, you're just applying some simple laws of physics to update the state of every particle every frame, and that way you're able to create really nice special effects like this. Alrighty. We could look at quaternion integration, but I think maybe we'll leave that until next week. Okay, everybody. Alright, let's leave it at that then. Okay, have a great weekend, everybody. See ya. Okay, well let's just have a quick update.